Earlier in this chapter, we mentioned regioselective reactions. And this is a reaction that forms two products from one reactant. More specifically, a regioselective reaction is a reaction that leads to the preferential formation of one constitutional isomer over another. So we start with A and we make B and C, but more B is formed than C. That is an example of a regioselective reaction. A stereoselective reaction is a reaction that leads to the preferential formation of one stereoisomer or over another. For example, we start with A and we make B and C, which are stereoisomers, enantiomers or diastereomers, more specifically. It could also be cis and trans stereoisomers. And through this reaction, we make more B than C, then that would be an example of a stereoselective reaction. Stereospecific reactions. This is a reaction in which the reactant can exist as stereoisomers. So in our reactant, we have enantiomers A and C or diastereomers A and C. And each stereoisomeric reactant leads to a different stereoisomeric product or set of products. So stereoisomer A reactant creates stereoisomer B product, and stereoisomer C reactant creates stereoisomer D product. So we're not saying that C and D are stereoisomers, we're saying that B and D are stereoisomers. The reactants are stereoisomers, and therefore the products are stereoisomers. Okay, so some products do not have some reactants do not generate stereoisomers. So 1-propene making 2-bromopropane does not generate a stereoisomer. Why? Because it does not have an asymmetric center, and it does not have a double bond to have cis-trans stereoisomers. So how do we know it doesn't have an asymmetric center? Well, look at the 4 things bonded to the carbon 2. We have a methyl group. We have a bromine. I'm going to list them in order of priority. We have 1 bromine, 2 methyl, 3 methyl, and 4 hydrogen. So because 2 of the 4 groups bonded to the carbon that could be asymmetric are identical, there are actually only 3 unique groups, and so no asymmetric center. All right, so how do we know when we are going to form more than one product from one reactant? The key is that when we form the product, if the product we form has an asymmetric center, then that will generate what we call a racemic mixture, or a pair of enantiomers. So the product will then be, if we have an asymmetric center in the product will be a pair of enantiomers. See if I can actually get the pen this time. Pair of enantiomers, if it has an asymmetric center. So then in your homework, that if the product is going to have an asymmetric center and they ask you to draw all possible stereoisomers, then it would be incorrect to draw your molecule without using wedge and dashed bonds, because we cannot express the presence of an asymmetry of two molecules using flat structures or only zigzag single bonds. So the actual products of this reaction of 1-butene with HBr are R2-bromobutane and S2-bromobutane. So why is a racemic mixture formed? In this reaction, it is because we go through a carbocation intermediate. At the step where we have the carbocation intermediate, the bromide ion can add to either the top or the bottom of the empty p orbital that will exist when we have an sp2 carbon. So if the bromide adds to the top of the empty p orbital, we produce one isomer, and if it adds to the bottom of this empty p orbital, then it produces the other isomer. So if it adds to the bottom, it produces this other isomer. And in that way, we produce both S2-bromobutane and R2-bromobutane. So starting from an alkene, where the more substituted carbon will end up with 4 different groups. If your alkene has 3 different groups on the carbon that will bond to the halogen, then you can tell that once the halogen bond forms, that will make the 4th different group. You have an asymmetric center, and you will make a racemic mixture of products. And you must draw both products to give the absolutely correct answer for that question. So forming a racemic mixture. If the reactant does not have an asymmetric center, and the reaction forms a product with an asymmetric center, the product will be a racemic mixture. So that is a rule that you need to know and be aware of. You cannot forget this rule. Examples. 1-pentene reacting with under acid catalyzed hydration conditions, which puts an OH at the more substituted carbon. When we put an OH at the more substituted carbon, we end up with propyl, methyl, hydroxyl, and hydrogen. That's 4 different things. That is an asymmetric center. So this acid catalyzed hydration of 1-pentene produces a racemic mixture. What happens if we start with 2-pentene instead of 1-pentene? And we start with, if we start with E2-pentene and we do acid catalyzed hydration, we form one product with one asymmetric center. If we start with cis or Z2-pentene and we go through the cation, at the point that we form the cation, the cations for E and Z will actually be identical. So the cation carbon is sp2 hybridized with an empty p orbital. The water can add to either the top or the bottom of the empty p orbital, which produces 2 isomers for the product, giving a And that is clear because we know our product should have two isomers if it has an asymmetric center in the product. Where there was not an asymmetric center, a carbon with 4 different groups or an atom with 4 different groups in the reactant. And these reactants do not have a carbon that has 4 different groups. Forming a second asymmetric center. So if we already have one asymmetric center, and in our product we form a second asymmetric center, the asymmetric center in the reactant that was not part of the pi bond is going to be unchanged. So it will have the same configuration in the product as it did in the reactant. So all products will then have one asymmetric center that has the same configuration. And if we generate a new asymmetric center in the as a result of the reaction, then we will create both the R and S isomer at that carbon, and we'll create two molecules that have one carbon with the same asymmetric configuration and the second carbon with different asymmetric configuration, which means we've created a pair of diastereomers. So the rule, if we have one asymmetric center in the reactant and we form a second asymmetric center as a result of the reaction, then the reaction forms a product that will be a pair of diastereomers. Okay, so an example of a reaction that forms a product with a pair of diastereomers, taking a 1-pentene with a methyl group and on a solid wedge and a methyl group on the pi bond. If I do hydroboration, then in hydroboration, we'll add a hydroxyl group to the sp2 carbon of the pi bond that has fewer bonds to carbon. So on one of the vinyl carbons, we would have an OH group, and on the other one, we would still have our methyl group. What you need to remember with hydroboration is that we are adding H and OH to the pi bond, but they have to be on the same wedge type. They have to add syn. So that means that if OH and H add syn, then the methyl group will be anti to the OH, the methyl group that was on the pi bond. So in this case, we have one asymmetric center that is not part of the chemistry. So we're not changing this carbon. It doesn't have a pi bond. It's not interacting with the reagents. It's unchanged. So the configuration of this solid wedge carbon at the top is undisputable. But in the product, because OH and H can add to either the top or the bottom of the pi bond, dashed indicates it added to the bottom, solid indicates it added to the top of the pi bond. We get we get a new asymmetric center at the carbon that has a bond to OH, and a new asymmetric center at the methyl group. So we have 3 asymmetric centers total in the product. One that already existed, and 2 new. The one that already existed does not change. The 2 new will generate products where will result in a total of 2 products, and in one and with very specific configuration, because the OH and the H have to add syn, and we would have to do the 1, 2, 3, 4 counting of the groups and labeling to figure out whether those asymmetric centers were R or S. Okay, so if we look at the solid wedge OH, hydrogen is on, if OH is on a dashed wedge, then hydrogen on that carbon is on a solid wedge. Whoops, should be black. Okay, so looking at this yellow highlighted carbon, really? Because OH is the high priority group, but it's on the dashed wedge, I'm going to rotate it. I'll flip the molecule over. So I'll just flip the entire thing over using my mind and redraw it. So if I redraw this flipped over, what I'm going to have is solid wedge OH over here, dashed hydrogen, dashed methyl group at that top carbon because I flipped it over, now it's pointing backwards. Dashed methyl group over here, and the solid H. Okay, so these are the same thing. So looking at the yellow carbon, we can now label our priority of functional groups. O is 1. Okay. This carbon is 2, and the reason that it is 2 is that I have a methyl group branch 1 bond away, going in the clockwise direction, where I have a methyl group branch 2 bonds away going in the counterclockwise direction. So this group is 3 and the hydrogen is 4. So going in this direction, this yellow carbon, it has a configuration of clockwise or R. Now, to do the other carbon, I would look at the original not flipped over molecule, because for the green carbon, the hydrogen, the lowest priority group H is on the dashed wedge. So in that case, the highest priority carbon is the first carbon away is that methyl is CCC. So the hydroxyl group carbon has a priority of 1 in numbering. The so going clockwise from the green carbon, the first carbon out would be priority 1. Then going counterclockwise out, the carbon is 2. And then going down to the methyl group off of the green carbon, that is 3, and the hydrogen is 4. So that carbon is going in the clockwise direction as well, and that is also R. So this is R, R, numbering wise, the OH carbon is carbon 1 of the ring. So 1, 2, 3, 4. 1R, 2R, is what I have determined so far. And then the carbon at the top that doesn't change configuration between the two groups, labeling the priority of the groups. If I take the carbon, looking at this structure, I can number it. Solid, solid. So we have 1, 2, 3, 4, 5 for numbering. And for carbon, we're looking at the asymmetric center at carbon 4, and we're determining the priority of groups for the asymmetric center at carbon 4. So carbon 3 would have a priority of 2 for carbon 4. Carbon 5 would have a priority of 1. And the methyl group would have a priority of 3. So we would be going from 5 to 3 to methyl, and that is counterclockwise. So the top asymmetric center that is unchanged is has a configuration of S. So this is 1R, 2R, 4S. Cyclo 3,4 or 2,4-dimethyl cyclopentanol. 1R, 2R, 4S. 2,4-dimethyl cyclopentanol. Oh, that was hard. Okay, so that's like an example where, and then in the so how does that differ from the other isomer generated? What it is that we have completely opposite configuration in the isomer, in the stereoisomer generated at carbons 1 and 2, but the same configuration at carbon 3. So once we determine the configuration for one stereoisomer, the configuration of the other stereoisomer is clear. And I'm going to circle it in yellow. So this stereoisomer circled in yellow would have the name 1S, 2S, 4S, 2,4-dimethyl cyclopentanol. All right, so just be aware of the relationships between the product and its isomer and the asymmetric centers generated. Whew, we have some more examples. Okay,